first, we assume no storage is used outside of the hash table. Okay, so this assumption exclude the linked list approach. Okay, if we could use linked list, like the resolving the collision is easy, right? So because like we assume like we don't use the storage outside of the hash table, then the linked list is approach is not possible. So we need to insert the record systematically. Okay, so we need to into the table. And remember that, okay, not only we need to do that, but also we need to make sure, okay, after the insertion, this record can be searched, okay, can be found at later time, okay, also conveniently, okay. So basically, okay, an idea is what we call open addressing. Okay, basically, okay, we keep looking for what we call like an empty slot, okay, to place this new record. Okay, so hash function will depend on the key and the prop number. Okay, so it's going to be u times 0 1 blah, blah, to n minus 1. It will be mapped to a location in your table. So this is like your key, obviously. This is like the number of prop. Okay, so prop sequence, okay, should be a permutation of from 0 1 bar to n minus 1. Okay, because like you want to be able to cover all the empty slots in the hash table. Okay, and the table may fill up, and deletion may be difficult. Okay, it's not impossible, but it's this open addressing, like the deletion is like relatively difficult because what should I say, like say I will get to this point later. Okay, once we have an example. Okay, so for example, open address. Okay, so insert key k equal to 496. Okay, at the beginning we probe, okay, this location. I mean, here, okay, we are not, we haven't discussed like what the hash function looks like. Not yet. Okay, so assuming at the beginning, okay, this H496 0 probe, okay, is mapped to here. So it has, this space has been occupied by another record. So then we try H4961. Again, it gets mapped to here. So there's another collision. This space has been taken. Okay, so then finally, okay, 4962. Okay, this is the place that has not been taken. So we can insert the new record here. So this is like basically we just take turn. I mean, well, basically like increment like the prop number, okay, in the hash function. If there's a collision, okay, we keep looking for like a place to put this new record. Okay, so with this, okay, example now, okay, let's consider if you want to do deletion. Remember, say we delete 5A6. 5A6. So 5A6, I mean, well, the search basically takes place similarly, right? So once we find 5A6, we get rid of it. So this space become like a pink, right? It become empty, right? Now, when you want to find the record 496, okay, what happened is that you first, again, I mean, it's going to go through the same process, right? So first, like, oh, there's a collision, and then the next one. Okay, remember, this record has already been deleted, right? Okay, when this record is deleted, okay, you will start the search, usually in the open addressing. Okay, basically you keep looking for the record until an empty slot has been found. That's, I mean, natural, right? That's natural. But in this example, we have an issue because this, I mean, what if you delete this one? I mean, this is empty. So we tell, oh, 496 is not there, but it is. It is actually here. But because previously this one was empty, so you don't get to find this record. Okay? So how do we deal with that? I mean, there are some, some tricks we can play. For example, we can tag. Say like, oh, we delete this, but there are like additional record beyond this one. Okay, we can have a tagging. Okay, something, but it's like complicated. So it's not impossible, but it's complicated. It's complicated. Because like, search basically uses the same prop sequence. Terminate successfully if it finds the key, obviously. And unsuccessfully if it encounters empty slot. So it is because of this the deletion has some issue. It will affect the following search, okay, in the open addressing approach. So as I said, here we just use this to demonstrate the idea, but we really haven't discussed this H function looks like, right? We haven't discussed how this H function looks like. So this open addressing, they are, this probing strategy, there are different strategies. The first one is the linear probing. The linear probing is so easy. Okay, basically it's you just use the previous hash function that takes one argument, and then add I into the result. That's it. Okay, where I is the number of probe. Okay, so in other words, okay, say after the first collision is here. The next one will happen right after this one. Okay, the next one will happen here. Okay, if the key, if the next record to get inserted happen to be here again, remember this one has been taken, right? So it will be, oh, there's a collision, so we go to the next one. Oh, this one has been taken. So we go to the next one. Oh, this one has been taken. So it will be here. Okay, so you can see that, okay, this linear probing, this method, generally produces excellent results because it's easy. And this one. This method, okay, is simple, but suffer from primary clustering. That is what I was talking about. Like a lot of records get like to be placed like consecutively. Okay, so your table will look like some places are empty. Okay, with some places has a very low density, but some places has very high density. So it's not the density is not evenly distributed. Okay, in the table, we call that primary clustering. So where long runs of occupied slots build up, increasing the average search time. Okay, so moreover, the long runs of occupied slots tend to get longer. Okay, that is what I was talking about. Like the next one you put here, right? Okay, and then the next one, okay, because if it happens to be here, okay, the next one. So this one is taken, so you put here, and the next one, if assume it's here or anywhere here. So because this place has been taken, so you go here. So you see like a lot of records that are placed like consecutively. This is like the issue with the linear probing. Okay. How about the other one? The other one is the other strategy called like a double hashing. In the double hashing, okay, you have two hash functions, h1k and h2k. Okay, so your hki is going to be h1k plus I times h2k mod n. Okay, so here, okay, in order to make sure with the increment of I, okay, this thing is going to exploit all the space in your hash table. You have to guarantee, your h2k has to be relative prime to n. Okay, in order to make sure that happens. Okay, so one way is to make n a power of 2 and then design h2k, okay, to produce only odd numbers. So this is again, one way to guarantee that. Okay. So here, okay, we need to analyze the performance of open addressing. Okay, we make assumption of uniform hashing, even though it is difficult to achieve. Okay, as I said previously, but let's assume it's uniform. We have uniform hashing, simple uniform hashing. Let's assume this right now. Okay, how do we achieve like a uniform hashing? Like it will be advanced material that we will discuss next in the next lecture. Okay, well today, but it's going to be next lecture. Okay, another slide. So each key is equally likely to have any one of the n-factored permutations as its probe sequence. Okay, that's like what we meant by uniform hashing. So here's the thing. Given an open address hash table with low factor alpha, it's going to be n divided by n. Okay, smaller than 1. Okay, where n represents number of records. Okay, in the table, n represents the size of the table. So the expected number of probes in an unsuccessful search is at most 1 divided by 1 minus alpha. So how do we, analyze it? A lot of time, analysis is, how should I say, it could be straightforward. Okay, it could be straightforward. I know a lot of students in our department are afraid of analysis. Okay, my background is my undergraduate degree is mathematics, but to be honest, I changed my major into computer science in the graduate school because obviously my math wasn't that great, right? Yeah. So really the analysis is not really difficult. I mean, this is one example. It is really not that difficult. Okay. So for example, okay, you have to do one problem, right? You have to do one problem. That's k, 0, right? hk, 0. Okay, that's the first one. The first one. That you have to do that, right? And then with probability n divided by n, the first probe hit an occupied slot, right? That's easy, right? Okay. And the second probe is necessary. Any question with that? Any question with that? This is very simple, right? So, it's going to be, okay. 1 plus, okay, with this probability, you need, because there's a collision, okay, you need to do one additional probe, right? And then, again, you may have collision, right? Okay, because you have used one space. And the probing makes sure it's going to explore different locations, right? So it's going to be n divided by 1, okay, and the denominator n divided by n minus 1. The denominator is n minus 1, n minus 1. So with the same logic, right? Okay, you have collision, so it's going to be another parenthesis with. So you keep doing that, blah 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 blah. Any question with that? I mean, anybody can make this list, make this equation, right? So it's really not about mathematics. It's just, what should I say, high school math, right? High school math, or even because this equation is not any. Of course, at the end, okay, the last term is going to be this, right? Okay, because obviously I mean, additional term, I mean, the numerator is going to be 0, right? Okay. So this will be the last term. Okay. So we know and for each one, n minus I, okay, n minus I divided by n minus I is going to be smaller than n divided by n, right? When n is smaller than n. Any question with that? Again, it's a simple high school math, right? Any question with that? 譬如说我想说，五分之三好了，你上下各减掉一个数字，是不是会变小，对不对？3/5，你各减1好了，变什么？2/4，0.5，0.5是不是小于3/5？有没有问题？这个大家都可以接受吧 ？Everybody can take that, right? Okay, so we have that, right? And this one obviously is alpha, right? Okay, this is alpha. So, we have this, right? So, because, okay, we are replacing these terms with a bigger number. So this is going to be smaller equal, right? The above formula is going to be smaller equal to this one, right? Right? And then you can expand it. You can expand it. You know, you can really expand it. So it's going to look like this. Of course, here, okay, it's interesting because at the end there's because we have something that terminates here, right? But here, okay, you don't need to care about that. You can add some additional alpha to a certain power here, because it doesn't matter because this is an equality, right? Adding a few terms at the end, as long as those terms are larger than 0, it doesn't change the fact of this inequality, right? 就是小于等于嘛，你后面再加几个项进去，不会影响它，对不对？ So you can treat it as an infinite series. Okay, although we know it's not infinite, because it terminates at a certain point here. But it doesn't matter, once you replace it with alpha, we know that at some point, alpha to a certain power, it will stop. But that's fine, we can add additional terms. It doesn't matter, right? So if you treat it as an infinite series, because this is like a geometric series, so it becomes this. And you're again, probably not high school, probably like 你从这边到这边，你什么？国中学的吧 ？Junior high, right? Junior high or senior high? Senior high. But anyway, from here to here is easy, right? So analysis is really just like that. No, not a lot of depth. Okay, as long as you know how you are not afraid of listing this equation. Okay, then it could be easy. Okay, it could be very easy. Of course, this proof, we still do not consider this is a rigorous proof. If you want a rigorous proof, more rigorous proof, the textbook provides a more rigorous proof. Okay? But I think this one it should be sufficient. Okay? It should be sufficient to show you that, the expected number of probes in an unsuccessful search is at most 1 over 1 minus alpha. And okay, if alpha is a constant, then accessing an open address hash table take constant time. Okay, take constant time. If the table is half full, that means alpha is 0.5, right? So then the expected number of probes is 2. is if table is 90% full, then expect number of probes become 10. Okay, so having said that, okay, obviously it would be if you use open addressing, okay, it would be a good idea to make sure your table size is, some constant times bigger than the number of records stored in the table, because it helps with the performance. Okay, I mean this is kind of like trade-off between the efficiency and the storage space, So, I mean, which one is more important? Of course, in current computer science per se, like we know, like storage is cheap, right? Storage is much cheaper, so we usually prefer, to provide like bigger storage to exchange for like faster, like insert and search. Okay. That's it for this lecture. Okay. So as I said, okay, today we are going to talk about, to finish this lecture and maybe finish half of the next one. Okay, and next time we'll finish the next lecture and maybe talk a little bit, hopefully finish another one. Okay, so that will be the range for the midterm. Okay, and by the way, I forgot to mention. Okay, I gave you guys, I already have the sample meter uploaded to an E-class, right? Because I remember like one student asked me about the sample meter. Yeah, I already did that, but keep in mind that the problems will be different. And the range may be slightly different too. Okay, because as I said, like the majority of the chapters will be the same, yes, but I changed some chapters from time to time, so that's like why I say like, the range may be slightly different. sample meter 有在上面吗？还没有。对。
没看。
我放在那个上面啊。
没有，我刚看也没看到。没关系，我下课的时候再问老师好了。
我有传出去了。
可能变草稿之类的。
你看一下，在那个114，哇塞114。
好。
的那个 line 的这个，有找到吗？
我看一下，等我一下。
应该几天前送的，可能昨天还前天吧，至少。
好，老师我看一下。
有找到吗？
有。
有吗？
有，不好意思。
所以你没有人处理。
对，我没看到这个，不好意思。那时候。
Yeah, sorry. TA will upload it now. Yeah, I thought the TA has done that.
This PPTs are also not in the EE class. It's hashing 1 and hashing 2.
Oh, so they are not in the EE class. Okay, I'll upload it. Okay, sorry. I thought like upload all the handout like before the midterm. Obviously, I missed some of the handout. Okay, okay. So this one is this actually is a little more theoretical. Okay, we'll spend time talking about universal hashing and the universality theory, and how to construct such a universal hashing. Okay, but keep in mind, okay, the universal hashing that I talk about here is not the only way to create a universal hashing. There are other ways to do that. Okay, so but the one that I show you, okay, later would be probably the easiest one. Okay, and then the last one is the perfect hashing. The perfect hashing, I don't think we are going to cover perfect hashing today. Probably we'll finish the previous three. Hopefully by I'm able to finish them. Okay, today. Okay. So let's take 10 minutes break. So here we'll upload the sample return, and I will also send these slides, these handouts to the TA right immediately. Okay? Yeah. So let's take a 10 minutes break.这两个handout，我现在送到群组，好不好？现在就说。
期中考试放一个，
他正在写。
我已经说这个快了。
或者说那个part2，那个写一下交通处小线，就他那个学分，你把那个被存起来，你知道在学分就是什么会出事。
那东西很抽象，你任何一个顺序错都会直接选错。
哦。像我上次就是我复述设计师，但是就是最后要回去做然后
你用那个 algorithm left。
Actually six.
可以原本是那个开头在 shift 之前，
total statistics.
最后一个开头就被换 shift 过来，开头是然后 algorithm
six.
algorithm 就出事了。
他们那个跟 logical 在选差的。
应该有。
left
哦，没有，你看他第32次
没差的，没差的。
到第32次就到 shift 之前，如果他开头
是 right 有差，是 right 有差。
对，你把那个用掉，所以他开头变平，然后如果他 shift 回来的话，直接用 shift 回来，不把之前的存下来的话，那他就直接出事。
找我吗？
那个我传3个 handout 给你，这样帮忙 upload 上去。
好。
好不好？就是 lecture 6、lecture 17跟 lecture 8。
好。
6、7、8。
先睡，对，然后醒来的时候就写，醒来就来写。
老师，我只有看到7跟8而已，我只有看到7跟8而已。是，我再看一下。我看一下记录。啊，他没有送出去。有可能再按一次那个圆圈圈。
还在想这个翻出来的简单一点，想会一个交互100，标50，还是进度他这里在写作业，他其实不喜欢，干我就慌乱，
他其实在宿舍里写作业。
你可以用那个 step by step，自己可以语调的。
我好像说了一步一步执行，就是发现错在哪里。
其实这样一个意思是，不是话是就有小孩有点数学真的，
有写到那个错误，我不喜欢这八杠的，
我也不喜欢这个，
我不喜欢这个，我不喜欢这个，有些八杠在，而且你既然用 Visual Studio 想个方法出来，然后要code 之类的，我不知道它反正就是它有3个，因为它绿色的开始我觉得说的是，我觉得都可以啊，是干嘛？一定可以自己报，
这样讲的，你说 Studio 是你这辈子会见过最重磅的文字编辑器。
它没有太多。
身为文字编辑器，但是容量高的文字。
我好像写。
它有
只有是对啊。
你看啊，然后他
不是进来。
哦，
第3节会中
间不能动啊。
绿色这个没有啊，这里都可以到，你可以把这个分析。
对啊，但是这条不是错的。
对。
那个是他们的菜，我只是把它改到。
没有那个AI 而且
那是高阶机器。
就像是
可以直接让你的程式码换成一起。对啊。
在入的这边
LI，
在网上找，
你 LI，
然后都
中文是 LI，
然后我也觉得，
对，LI，
下礼拜老师刚刚上课。对，但我拿到。
哦，有水。
我不知道老师怎么办，老师进步所以哦，怎么开始？
再摔一次，
帮他摔一下，他受伤。
没有，这个时候可以用打火机烧一下，让他先他去。
没有，你摔一下是让他卡住，那你再摔一下就卡回来。哦。对吧？那个拿先拿雨伞之类。哦，对了。
这又是谁教你的？
老师有什么意思？
然后但是摔了第一次坏，第二次好，然后摔第三次。
你也没给
它爆开了，它的钢珠不见了。
这是T1吗？你这里要做T1，你是 Y。
没有笔记。
哦，好，这边。啊，为什么看不到这些？
为什么你的？
为什么你的这么？
不是，这里这样类似于一点。如果你的东西太大，不要的，我看他别的地方太多。
为什么看哪里太高？像是
天房。
是吗？有字天书哎，赚了吗？
哇，你自己上面也是写照你不知道是怎么做的，不能是我打的。这个就是你看他，可是这个是会过的。什么叫会过？我不知道为什么，反正他会过。
只要可以跑啊。
他可以跑啊，他会过跑到一半就停。不会啊，另外一个不会啊。哦。
Bro, what the fuck is that？
我看。其实卡在哪？你前面有输入吗？
你知道你现在这个看起来像什么吗？那个用脖子在飞的那个鸽子。脖子当那个螺旋桨在飞起来的那只鸽子。
反正动在飞。
什么东西啊？
我说，
不是，
我
我加一点
为什么要先出十？
因为我
干嘛不出十？因为为什么我不加抗拒？因为我他妈加完之后，我就发现干嘛都是抄他的，没有意思。就是很多就是直接复制他的东西然后发下来，就他某个区块对他做出十嘛。啊？我说我这个我从来都不出十。反正我的我也该看一下。因为我怕我不出十，他就跑掉了。那厉害。这上面也没有问题，这是没有问题。对。跟第一个很好的。所以你现在确定它都是正的？
非常小，我已经忘记我怎么写的了。不该在他妈凌晨3点写重点的东西。
不会打开发现，我是以前像填网页。
没有啦，我有乖乖加 comment 啊。
你有乖乖加什么？
我有乖乖加 comment 啊。
你全部能打成11。我看看，我有加。这个。我都没有。
啊，反正你到时候 demo 再看得懂就好。看不懂的话，现在赶快加一个comment。
我看不懂啊，我想要看懂。
我就是照着他的流程图做而已啊。
我完全没有照着他流程图下去靠背啊。
我就是照着他的流程图。
我想说他要我干嘛，然后我就自己干嘛了。就像我不照着他流程图的话，应该不会生气。
知道。
应该
他不是说 no requirement 吗？只要过 test case 就好了。
我觉得他照着他流程做，可是我不知道他会学到统计学。
我们要不要先看一下？我们先回那个 PPT。
你说
那个对，好，
这个
好，对，我们先看一下那个，他跳的 error 是什么 ？error 其实
爆炸。
对，所以158是哪里？
啊，就是158。
对，158，所以我们回那个 text，不是 text，然后看一下
这个小问题，
哇不是啊，白痴哦。BQ。
我是纯做西装的，我两个好像不太一样的东西。
白诺雀感觉比起来，
这个吗？
这一行，
这边吗？
哇，不是，
看一下
这个要68对应的是184哦，应该是这个，
我的后排。
168。
68对
BEQS 2翻到圈的分数。
哦，是这个，
这一行啊，
这个问题，
这一行炸了。
炸弹小。这是最不可以炸的，这他妈这个差别是有点丑。
S2是那个啊。
它的 S
S2，S2是什么？你 S2是啥？
我写在上，我写在上面。
哎呀，我有写注解，我有写我每一个是什么，我只有写这个。
S2是那个记录第一个东西的字符嘛，我记这个比较准。
dependent。
对。
那个跟做 demo 的时候你就这样 dependent。
妈的，以为那个骂我们。
它是
讲一讲，突然变成咖喱味。
然后加第一个丑。
只在确认它的那个符说要加这个符号。
如果它是负号，如果它是负的话，
如果它是对
低出的，
然后就把它翻过来。
对啊，那一做它
N3就是那个
另外一个
引发一个。
如果它是负的，然后它是正的，负的正的它就不调了。
你为什么两个要用相反的逻辑？
因为
对啊，为什么要一个 P 一个 B？
我不知道，因为我俩字写的时候应该是分开写，我可能是去床上躺一下，然后再出来。
你妈！为什么有人是用 BQ1，然后一直有人用 BND？我知道都没错，但是你他妈
你还写嘛？
你干嘛？你知道你是三小？
我比较喜欢用 BQ，因为它正着看跟电脑看都一样。
我也蛮喜欢 BQ，但我有时候又想说，我觉得反正看好像也可以。
你电脑看一看。
但看我当下脑袋想怎么开？
看你这个真他妈的是疯狂乱
所以
写。
这也是，如果它是负的，
无限
两个都负的，就会变到这里。
对啊，这个是负的嘛，负的到负的完到
去负的会开3。
负的除负的当正。
对啊，负的除负的是正的，
然后余数要
没有，这段一定没有问题，因为我
翻到圈
另外一个做起来是对的，但是我光
为什么你翻到圈 portion 是用？老板，你这个，如果你
当我听到有人看老板，就是代表他急了。
应该是你的 S3跟 S2吧？不是老板，
对啊，我看一下我在那边写的什么，我在那边是笨的，我不知道什么事。
因为你这个才会有这个问题啊，你这个语数才会有这个问题。
你不是一样的，他们在这做学习啊。
对啊，但是你这是啥？
是不是写错了呀？我看了。
我都很关我做什么，我全部都有，我都有 comment 靠背，
我有 comment 啊。
对吧？
你那个是不太清楚了。
不是啊？
对，
那你提问呢？提问是语数。语数跟零比，语数。
哦，你这边已经做完一次
零减语数。
那这个0跟1是那个啦，它是负的还是1，好像是正的。
我觉得你 S2以前是有覆盖的。
不是，等一下，这个重点是为什么？如果两个都负的话，你过去还是靠的。
两个都负的，
过去跟那个 dividend 跟 divider 两个都负的话，你过去还是靠这个。你负是除负2，你出来是几个？2。对啊。那你为什么这个是它跟零去哪里过？
负的除负的是正的，但是语数是负的。
然后说所以你的过去就是
所以我写了4个 else。
我操！所以你的 quotient 为什么是
负的，
divider 跟零去做哪里口？
负的都会不会是负的？
好像少一个。所以我写了4个好常见。
就是你负的。
不是这么写。
不是，这为什么要？重点是为什么它这一卡？
他应该可以用 XO 啊。
因为它不该卡在那里啊。因为它在那边对的，我用同语词啊，在那边是对的。
它不该卡。
我跟你写类似的。我是 quotient， 它是 S203，但是我原本是选 S203这样。
分母是封掉了，
爆掉了，
下不来了。
Explorer 的 exe 之为，然后就重开了。那为什么你会爆啊？
土豆啊，
为什么你卡偶尔还会爆？
为什么
你卡偶尔还会爆？什么鬼啊？啊？而且是那个 integer underscore 吗？那个是 integer underscore 嘛，对不对？name underscore，你再跑一次看一下。
overflow。
这样，修下来。后面怎么那么精彩？
对。后面。
他说
这样。
但我觉得其实我是除法不会，你知道吗？我昨天还特别想一下，我觉得我除法好像真的忘了，我真的已经忘了这个。忘记除法。我不会除复数啊，干复数他妈的那个，都嘛只用分数，谁他妈在把它算出来的？我直接除到忘了。
没有人会留语数。
确实啊，上次留语数大概是国小会复数留语数吗？
我有复数。
啊，
不会留。
国小会叫你写点点点的语数。对。
哦对，国小不会有妈的复数，到复数存下去不会问你复数。
付出正等于什么？付出正正乘负等于什么？付出负等于什么？
那天真的问我在国小的那种说，那你有没有学过公正正？
正正得负。
你没回一个正正得负怎么办？
就
那我就跟他说，做得好，以后当数学家。都认同那个会是，你有出吗？
你有见什么样？啊，怎么说？
对，有出的。哦，对，你的这个，你要不要先改一下？你要不要先改一下博学那一边？照理说是可以跑的，
我要思考。
没有照理说是可以的。
不是你把那个零改成 S2 就好了。
没有，而且重点
不是，我不知道这个除法这个语数的定义是什么。我怕他现在的定义就是，如果它是负7，然后他要去除负2，那他就是一直给它加负2，加到这个出来，那个号变得跟原本不一样。
我再弄回去。
那我得写。那你干嘛？
其实最简单就是。
他就一直扣到不行的时候再把它加回来。
最简单就是语数会用这个，然后这个就是它前面两个。
这个。
exclusive or。
不行，我要打错我的写法。
然后去加2，加到变正义的时候，然后
你要点来看点数。
我要大推我的写法。
4个条件
4个 Excel。
不是，你这样写就好了。
然后它会有 positive negative positive negative。对，那个。
不是，这样不就好了？
没有，我这样可以 Excel 或者是什么？
这样就好了。
可我不要，操！我是弱智。
OK， 好。好，我们继续哦。那个不对，对手用中文。对。So let's continue. OK。So first, the missing handout have been uploaded, okay, to E class, okay. So including this one, okay, please check the E class, okay, and I apologize for like forgetting about that. I haven't decided like which chapter to cover, like in addition to this one yet, okay, but I will, make my decision and upload the last one, like, that will be covered by the midterm, like, later today, okay. And by the way, like, I know like tomorrow is actually like a beginning of the spring break, so it's a pity that this class is not affected by the spring break. I mean, like, I was hoping like we could have a few days off, but this semester it looks like this class is not going to be affected by any holidays. Okay. Okay. So we know like we already discussed the choice of hash functions in the previous lecture. I'm talking about not like last week. I'm talking about like in the last slide. Okay, the previous slide. Okay. So even though we assume like a simple uniform, okay, property, but it is difficult to achieve. So actually, we know like for any hash function h, as long as the hash function is determined, okay, as long as you have a fixed hash function, okay, a set of keys exists that can cause the average access time of a hash table to skyrocket. Okay, basically you just try to, because like, once the hash function is determined, you can try to, select your key such that all these keys, after they are transformed, they are, converted by hash function. Okay, all these keys, okay, after like applying hash function, they all collide. Okay, so in other words, like it's going to be something like all these keys, like such that hk equal to I for some slot I. So these keys are all collided. Okay. So if that's the case, obviously, like you need to deal with like collision resolution. Regardless what collision resolution we tried, okay, there are like inherently like additional overhead. So that is why like we say like it's going to cause the average access time to skyrocket. Okay. So what do we do? So because the key point here is that once the hash function is determined, we have this issue, right? So a good, an intuitive idea is just that we do not have a fixed hash function. We choose hash function at random. We draw the hash function from a set of hash functions. Okay, so this hash function is chosen independently of the keys. Okay, so even if an adversary can see your code, okay, even someone is able to observe that you have a set of hash functions, okay, because the attacker doesn't know exactly which hash function will be used, Okay, because this is like a random selection. So at the end, the attacker will not be able to find a bad set of keys to collide. No, intentionally. Okay, so that's the basic idea here. Okay, so the idea comes down to like we need to have a set of functions. We call this approach universal hashing. So let H be a finite collection of hash functions. So H is a set of hash functions. Okay, and it's finite. Okay, and that so each mapping U to the space of the hash table. Okay, so we say H is universal. Okay, we say H is universal if for all XY pair. Okay, for all XY pair. Okay, any choice of different keys. Okay, we have H, okay, the choice of hash function, okay, from this set, okay, to make Hx equal to Hy, okay, such a choice of hash function, the hash function that satisfies this property, that x equal to Hx equal to Hy, okay, is going to be smaller than the size of your set divided by n, small or equal to this one. Okay, so intuitively that means like the chance of collision between x and y, because like we choose the hash function randomly, right? We choose the hash function randomly. So the collision between x and y is going to be smaller or equal to 1 over n, because such hash function, the number of such hash functions is bounded by like the size of big H divided by n, right? And because we choose hash function randomly, so the choice, of hash function is the probability is 1 over big N, big H, sorry, 1 over big H, right? So 1 over big H times big H over N. So it's going to be, the probability of the collision is going to be smaller or equal to 1 over N. Okay, we choose H randomly from the big H. Okay? So if the H is universal, then we can guarantee the random choice of hash function will allow like the collision, the probability of like two different keys to collide. The probability is bounded by 1 over n. And then remember, n is the size of the hash table, by the way. So of course, at this moment, I have not told you how to construct such a universal hash yet. 就我还没跟你讲怎么样去建造这样子一个 universal hashing. Okay, but try to assume such universal hashing exists at this moment. Okay, later on I'm going to tell you how we can construct such universal hashing, and it is actually easier than you may think. Okay, so the theorem that H be a hash function chosen at random from a universal set H. So this h is already universal of hash functions. So suppose h is used to hash n arbitrary keys into n slots of a table T. Okay. Then for a given key x, we have the expected number of collisions with x is going to be smaller than n divided by n. So inserting n keys into n slots, the chance of collision, okay, the expected the expected number of collisions, okay, is going to be smaller than n divided by n. So how do we prove that? So that first that capital CX be a random variable that denotes the total number of collisions of keys in T, okay, in the table T with X. Okay, so this is total number of collisions, okay, with the key X. Okay, so that lowercase cxy, okay, lowercase cxy, this is an indicator, random variable, okay, to be 1 if hx equal to hy, and 0 otherwise. Okay, so this is like a, hx equal to hy obviously indicate a collision, right? Okay. So we know like expected cxy, okay, is going to be 1 over n, right? Because like this one comes from the property of universal hashing, right? The expected lowercase cxy is 1 over n. Is this probably comes from the fact that we draw the h at random from a universal hashing. Okay, so the collision, okay, for a pair of different keys, okay, the chance for collision for a pair of different keys is 1 over n, right? Okay, and the capital CX is going to be the summations, lowercase cxy, and where y, is t minus x. Okay, because we want to, the capital CX indicates the total number of collisions of keys with x, right? So you need to consider all the different keys that collide with x, right? So you need to add up all these lowercase cxy. So far so good, right? You guys with me, right? Okay. And then, okay, the expected value of capital CX, okay, is going to be expected value of like this summation, like basically just we apply summation on the both sides of the equation, right? Okay, and then because of the linearity of expectations, we can directly move the expectation into the summation. Okay, we do this many times previously already, so this is not like anything like complicated. And then and we know from our previous discussion, we already know expected value of lowercase cxy is 1 over n, right? That is like independent of the x and y. Okay, and then y is not not x. Okay, not x. So that will give you n minus 1, right? because the size of table T is n. We have n records, right? We have n records. Okay, so other than the record X, so the other Y's, they are n minus 1 records out there. So that's it. So n minus 1 divided by n. Okay, so that's it. So you see that, so this is smaller than n divided by n, because the result is n minus 1 over n, right? Okay. So now, okay, because the universal hashing is so nice, so we need to know it has a good property. So we need to know how we can construct such a universal hashing, right? It looks complicated, but at the end, it is actually easier than you may think. Okay, to construct a set of universal hashing functions. Okay, how do we do that? Okay, let n be prime. Okay, we still have 20 minutes. I hope to finish this part. Okay, so let n be prime. So we can decompose key k into r plus 1 digits. Okay, or you can just assume your key has r plus 1 parts. Okay, so each digit or each part, okay, with value in the set from 0 to n minus 1. Okay? So in other words, your key looks like this. K0, K1, blah, 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 to KR. And each KI, the value is from 0 to n minus 1. So each KI has n different number of choices, right? So far so good, right? You guys with me, right? Okay. So first, we can pick A equal to A0, A1, blah, 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 to AR, where each AI is chosen randomly from this set. Okay? And then we can define HAK, okay, to be the sum of AIKI mod n. Remember, n is a prime. Okay, n is a prime. Okay, n is a prime. So this HAK are the elements in your capital H. So we claim that capital H is universal. Okay, first, what is the size of this capital H? Because once these AI are determined, this hash function is determined, right? Any question with that? Once these AIs are determined, the hash function is determined, right? The variables of this hash function is the AIs, the A0, A1, A2, blah, 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 to AR, right? And each AI, how many choices are there? For each AI, you choose from this set. So you have n choices, right? You have n choices for each AI, right? So totally, because we have from A0 to AR, so we have R plus 1 number of AI to choose, right? So the high school math tell you the total number of hash function is n to the power of R plus 1, right? 你高中学的排列组合应该还没有完全忘记，对不对？对，每一个有 n 个嘛，你有 r 加1个嘛，对不对？啊 n 乘 n 乘 n 有乘上 r 加1次，是不是 n 的 r 加1次方？这个问题，高中的排列组合。Okay, I mean in this class we are going to use like some simple math, like simple probability or like high school math. Like, you know, I'm not going to, you know, bore you with like you know very like a deep mathematics. I mean, no. So this first, you know, like the size of this total number of hash function in this set is like n to the power of r plus 1. Do you remember this? Do you remember this? Because later on we are going to use this. So we need to, here we claim that the h, this capital H, that is composed with like a lowercase ha is universal. So what is universal, by the way? Universal means that, okay, if you have two keys, I mean, the number of hash functions from this capital H, okay, that make these two keys, okay, that will collide, okay, make these two keys collide to each other, is bounded by capital H, the size of this capital H divided by n, right? Okay. So that's assume we have two different keys, x0, x1, blah blah is r, and y is like y0, y1, blah blah to yr. So they are distinct because they are different. They are distinct keys. So they are different by at least one digit. Is that right? They are different by at least one digit. Right? So, I mean, W log is not log, okay? This is not log. It's without loss of generality, okay? Okay, without loss of generality, we can assume that you know, the digit 0 is the one that are different. Okay, if they are not different at digit 0, we can swap, right? I mean, so it's okay. Like so we assume the position 0, they are different. So x0 and y0 are different. Okay? Okay? So how many HA in this capital H do x and y collide? So for these two, for them to collide, we know HAX has to be the same as HAY, right? Right? That's the collision definition, right? Okay. So that, I mean, according to the definition of the hash function, that means this one, right? AIXI, okay, summation, is equivalent to AIYI, you know, mode n, right? This is like, you know, the definition of the collision, right? Okay. So far so good, right? You guys are still with me, right? So we need to see like how many choices of these AIs can make this happen. Okay. So we can move like the right side to the left side, and you know, to be like this. It's easy, right? Any question with that? 这个应该很容易接受吧？我们只移过来嘛，然后把它稍微整理一下。Okay, just okay. And then because the first digit is different, right? The first digit is different, so we know this term must not to be 0, right? The x0 minus y0 must not be 0, right? I mean, I'm not saying a0 is not 0. No. I'm just saying x0 minus y0 is not 0. As for whether or not a0 is 0, we don't know. Okay? I'm not saying anything about a0. The only thing I say is a0 and x0 and y0, they are different, right? Because we assume, I mean, the x and y are different keys. So without loss of generality, we assume the first digit, the first position, they are different. So the x0 minus y0, they are different. So this part is non-zero. Okay, and then we have the rest of terms are here, right? The rest of terms are here. And then we can move the rest of terms to the other side. So far so good, right? So far so good, right? So this one, here's the catch. Okay, we have a theorem that n be prime for any z, okay, such that z is not 0. There exists a unique, the inverse, such that z times z inverse, equivalent to 1 mod n. We know that, right? From your discrete math. I hope you still remember. If n is prime. 谁教你们那个离散数学？啊？蔡老师。OK， 记得这个吗？没有人点头哎。Nobody nod. Okay, fine. Okay, I told discrete math early, a long time ago. I will prove this to you, okay, for you. Is that okay? Is that okay? But at least you know one thing, right? If two numbers are relatively prime, if two numbers are relatively prime, say, if P and let me just use the notation here. If N and Z are relatively prime, then there exists A and B such that then there exists A and B such that A times n plus B times Z equal to 1。这个记不记得？也不记得，感觉比那个还不记得，比这个还不记得。好，那我再给你们一个 keyword， 辗转相除法。Okay, sorry, I don't know the English term for that, but yeah, but at least like I mean, 两个互值的，你可以这样子除，这样再弄，到最后会有一，对不对？那你把它反过来，弄回来，可以变成这两个的那个乘上这两个数字乘上 A 跟 B， 那个线性组合起来变成一，对不对？还记不记得这个东西？辗转相除法。你不要跟我讲辗转相除法也不会，那我就没办法救你了。OK， 辗转相除法这不是大学教的，这应该高中就有教了，对不对？可能有些人是不是国中就有教了？对，好不好 ？OK， so if you have this, try to mold n on both sides. Try to mold n on both sides. This one cancel out, right? Because there's a n in here, right? Okay, right side is 1 and mold n, so so b dot z right? Right? So what does that mean? That means for any integer that is relatively prime to n, there's an inverse which is actually that b. Okay, that b is the inverse of that inverse exists. Okay. And also, like the next one is you have to prove this inverse not only exists but also unique. Okay, so it's like say if B1, B2. When you show that B1 I think this one is relatively easy, so I will leave this one to you guys. Okay, 这个相对来讲比较简单啊，因为你就移过来，然后做一下，这个应该相对来讲是比较简单的。因为好，我就直观跟你讲，我不用证明。就直观跟你讲 let me just tell you the intuition. Okay, this means what? This means z times b1 minus b2 is divisible by n, right? Right? 它们两个相减，一定可以被 n 整除嘛，对不对？有没有问题？这再有问题，我没办法救你了。那 n 跟 z 互值嘛，所以 n 只能从 b1 减 b2 来嘛，对不对？那就得到 b1 跟 b2 是 congruent to n。我就直观跟你讲，我就不用证这个其他的 ，OK， 好不好 ？So OK, so here OK, because n is prime, so any number OK must be relatively prime to n. So the inverse not only exists but also unique. Okay? So here is actually an example. Okay? Say n is 7. So if your z is 1, okay, well the inverse is 1. If z is 2, the inverse is 4. You can try, multiply them, and the mode 7 must be 1. If z is 3, then it's 5. 3 times 5 is 15. 15 mode 7 is 1. 15 mode 7 is 1. Okay? 4, 2. 4 times 2 is 8. 8 mode 7 is 1. 5, 3, 6, 6. 6 times 6 is 36. 36 mode 7 is 1. Right? So for every number, okay, the inverse exists and unique. Okay? 所以讲了这么多，好，我们快要结束了，给我2分钟可能不止2分钟，应该很快。Okay. So I just need a few additional minutes. Okay. So we have this one, right? We have this one. Right? What does it mean? That means that, if your, A1, A2, A3 to AR are fixed, then A0 is determined, right? Because A0 is the inverse of X0 minus Y0. 对不对？就是说，如果说你的 A1、A2 一直到 AR， 就是右边决定了，只要你右边决定了，左边 A0只有唯一的解，这没问题。If your A1, A2 to AR are determined, then A0 has only one possible solution. Okay, and this one, how many choices do we have here? How many choices do we have here? A1 has n choices, A2 has n choices, A3 has n choices, AR has n choices. Totally, how many choices? N to the power of R, right? And once you determine the A1 to AR, then A0 is uniquely determined, right? Because you want the X and Y to collide. You want X and Y to collide, so that's A0 is uniquely determined. So, any choices of A1 to AR, there's exact one choice of A0 that will cause X and Y to collide. So, how many HAs will cause X and Y to collide? There are n choices for each A1 to A2 to AR. So totally there are n to the power of R, this many choices. And why do we put 1 here? Because for A0, there's only one choice here. Okay? So it's n to the power of R to make X and Y collide. And this is exactly the size of H divided by n, right? The size of H, what is size of H? Remember? That's n to the power of R plus 1, right? Divided by n is n to the power of R. So, we have the proof. Okay, if we construct the set of hash function this way, this set of hash function is universal. Okay? 有一些是 some of this material comes from like a discrete math. I mean, how should I say? Like Professor Tsai will be very sad if I tell him about this. Okay, yeah. But anyway, that's it for today. So next time we will talk about perfect hashing and to finish up this chapter and then move on to the next one. Okay? Any question? 如果没有问题，我们今天就到这边好不好 ？OK，谢谢。